Okay, once again, good day, grade 10s, 11s, and 12s, and welcome back to the Anti-Science Theory. So in this video, we're just going to continue looking at electric circuits, still continuing to trying my very best to making it one of the best topics on your side, making it your most strong topics, right? By the way, so in the previous video, which if some of you have not watched, please make sure that you watch the first video. Just a little introduction with a few important points. Just you can actually get can actually watch that video. The link is down in the comment section, but sorry, in the description. Okay, so by the way, so in the previous video, we looked at the fundamental introduction of electric circuits. That is, we looked at the respective terminologies, right? Really, the relationships under Ohm's law, right? Which remember states that the potential difference across the ends of a conductor is directly proportional to the current flowing through that particular conductor. That is true if and only if the temperature remains constant. And we've looked at how current is directly proportional to the voltage and inversely proportional to the resistance, and the voltage is directly proportional to the resistance um, with a certain condition, right? And we've looked at different types of circuits, that is the parallel circuit and the series circuit. So what I want us to do now is just to know a few examples on series circuits as well as parallel circuits, and a few on combination circuits, right? Just to get quite familiar with this topic, just to familiarize ourselves with this topic. So I want to get first and foremost with the first example, right? So just want to do the first example. So example one. Okay, so example one. What do they give us? So in example one, no, do not do that. Oh, sorry, I'm just going to erase that. Okay, that's fine. So in example one, we get a circuit. Okay, okay. Trying so hard to have a very nice circuit to draw. Aha, there we go. And then here I have my emitter A2, and then here I have my resistor, and that resistor is a 2 ohm resistor. And then I continue to move on, and then I have a 4 ohm resistor. Sorry, that's 8 ohms. Um, that's my 8 ohm resistor, and I continue to move. And as I move, I meet another emitter here that is A1, and there we go, like that. And V8 has a voltmeter of unknown value. So V8 has its voltmeter here. So let's call that V2 and right there. And then the voltmeter across the battery is V1. And V1 reads 11 volts. Okay, so that is our typical circuit, right? So the three questions that we must answer, so they want us to calculate the total resistance, calculate the total resistance. They want us to calculate the reading on A2, and they want us to calculate the energy dissipated. So they want the energy dissipated by the 8 ohm resistor. 8 ohm resistor in exactly 4 minutes. Okay, so these are the questions that we must answer. Now, ladies and gentlemen, please promise me and promise yourself as well. Please do not break that promise. Please do not break that promise. Promise me that when you get to an exam, in fact, from here onwards, you normalize the habit of analyzing your diagram before you attempt to answer any questions. Please promise me that part. Make sure to analyze any of your given diagrams before you answer any of the questions, please do not make any mistakes when it comes to that part. So, what do I mean? I mean, in a typical exam, before you even look at these guys right here, before you even look at the questions that they're going to pose at you, the questions that they will ask you, make sure that you analyze your diagram first. Why is that helpful? That is helpful because it actually helps you in making the answering of your questions quite a breeze. It becomes very easy for you when you have to answer the questions that they ask. Right? So I'm going to show you how helpful that is. Right. I don't know why I made this um, highlighted. I just tend to just do some things from time to time. I'm so sorry. But anyway, so what is the first thing that you do when you analyze? Always, always, always show, start by indicating the flow of current. Okay. If you want to have that as like a young reminder for you, probably at the side of your book or a poster on the wall, do so. Just make sure that you always start by indicating the flow of current. What do you know about the current in a circuit? It flows conventionally. So that means it flows from the positive terminal to the negative terminal. So it's going to flow in that direction. So notice how before I even answer the questions, I am analyzing my diagram, right? I'm analyzing my diagram. And by the way, remember that in the first video, we said that a voltmeter has infinite resistance. So please, never ever do this in an exam. Do not have current flowing through the voltmeter. Current does not and will never ever flow through a voltmeter. This is wrong. Do not do that, please. Right? So make sure that your current never goes through the voltmeter. So it goes in that way, through there, all the way to the 2 ohm resistor, and all the way to the end. Right, so I've indicated my flow of current. Now, the importance of the flow of current is that it actually helps you realize, right? So it actually helps you realize that, I mean, it helps you actually identify, rather, whether your circuit is in parallel or in series or in both. And we usually call that a combination circuit. So what it helps you, the flow of current helps you realize whether your circuit is in parallel, in series, or it is a combination circuit. In other words, that means it's both, right? So in this particular case, what did you do? You showed the flow of current. And what do you notice? Do you guys actually agree with me when I say that A1 reads the total current? Because from the moment the current starts flowing, A1 read the total current. And when I say it's the total current, I mean there was no disturbance before the current reached emitter A1. The same current from the beginning is the same current through A1. That is why I say it's the total current. I really hope you guys can see that. Similarly, A2 also reads the total current. Why? Because notice how the current through A1 continued to move and reached A2 with no breakage, with no split. The current did not split in any way, right? That is the only time current starts to change, when there is a split in the circuit, right? So notice how the current was the same, it was not split or it was not divided. That is why I say A1 reads the total current and A2 also reads the total current. You'll see what this actually means when you get to parallel circuits. But notice something. The 8 ohm resistor. So notice how I'll start writing my analysis, what I observe. So I observe that A1 equals to A2, and both of them equal the total current. I'm writing down everything that I get from my analysis. Very important. Right. And then what do I get in my second point? Okay, I then notice that. Okay. Do you guys agree with me when I say that the emitter, um, okay, anyway, that 8 ohm resistor and the 2 ohm resistor have the same current flowing through it. So the current that flows through the 8 ohm is the same current that flows through the 2 ohm resistor. I really hope you guys can see that, because the current, like I said, current can only differ once there is a split. in the circuit. And in this particular case, there is no split in the circuit. Thus, the current through the 8 ohm resistor is equal to the current through the 2 ohm resistor. I hope you guys can see that. Therefore, I can conclude that the current I through the 8 ohm resistor is equal to the current through the 2 ohm resistor. Do you guys agree with me if I say these two currents also have the total current? Why? Because the total current registered by emitter A1 is the same current that flows through the 8 ohm resistor. And it's also the same current that flows through the 2 ohm resistor. And also the same through the A2 emitter. I really hope you guys can see that. So these two guys basically measure the total current. So these two also measure the total current. Notice how I keep writing down my observations. Do not forget to do that. Make sure before you answer any of your questions, analyze the diagram, right? And notice something. V1 has a reading of 11 volts. What did I say? I said in the previous video that the voltage read by, sorry, the voltage across the battery, so the voltmeter across the battery reads the total voltage. Thus, VT is 11 volts. So V1 is, so let me just make it very clear. So V1 is actually the total voltage. And what is V1? V1 is 11 volts. Right? So the total voltage is 11 volts. Notice again, every observation that I make, I write down. Every observation from my analysis, I keep writing it down because I know for sure it's gonna help me in the follow-up questions, right? So what do we see? So we now notice, okay, is there anything else we can actually analyze? Yes. I want you guys to notice something. In fact, let me ask you, do you think that if I had to introduce a voltmeter across the 2 ohm resistor, so if I had to introduce a V3, okay, terrible, terrible, terrible. So if I had to introduce a V3 here, do you think that V3 would be equal to V2? If you said yes, you are um please try to just look at the previous video and understand why it's actually a no, right? So if I so V2 is not equal to V3, but I hope you guys agree with me when I say that V2 is greater than V3. Do you guys see that? V2 has a reading that is greater than V3. Why? Remember, we said in the first video that voltage in a series circuit, wait, how do we know this is a series circuit again? The flow of current. Now we can easily and freely conclude that this circuit is series, right? According to the flow of current, the current was the same everywhere, right? Now, what do we know about a series circuit? For starters, the voltage across a series circuit is divided proportionally. That means the higher the reading on a resistor, the higher the voltage across it. So V2 has a higher reading than V1, I mean V3, this guy right here, this guy right there, right? Why is that? Because because the resistance for V2, which is the 8 ohm resistor, this guy here is greater than this guy. So the greater the reading on the resistor, the greater the voltage across it. So V2 is bigger. So notice how I start writing down my analysis. So I say my last point, V2 is greater than V3. Why is that? Because 8 ohm resistor is greater than the 2 ohm resistor. And notice how the V2 resistor, sorry, the V2 voltmeter is for the 8 ohm resistor. Another thing, a very important point, when you answer questions, Make sure that if you want to calculate, say, the value of V2, every voltmeter has its corresponding resistor. So V2 goes hand in hand with with the 8 ohm resistor. Similarly, V3 goes hand in hand with the 2 ohm resistor. However, V1, being the total voltage, is for the entire circuit. But what do you know? You know that V1 is going to be the sum of V2 plus V3. Hope you guys can see that. Remember, from the first video, you must be able to understand what I mean by that. V1 is the sum of V2 plus V3. Why? Because we say that voltage in a series circuit is divided proportionally. The greater the resistor, the more voltage. The lower the resistor, the lower the voltage. So 8 ohm is bigger than 2 ohms. Therefore, 8 ohms will have a high voltage. Similarly, 2 ohms is bigger than, I'm sorry, once again, let me actually repeat, 8 ohms is bigger than 2 ohms. Therefore, 8 ohms will have a high voltage. Therefore, 2 ohms is smaller than 8 ohms. Therefore, V3 will be having a voltage lesser than the voltage of the 8 ohm resistor. Right? Notice every voltmeter has its corresponding resistor. Right? So that's a very important point. Am I done with my analysis? Yes, for now. For now, it's safe to say I'm done, right? So, and now I can start answering the questions. So what does question A say? So A says to me, calculate the total resistance, right? It wants the total resistance. What do we know? So since these are resistors in series, we use the equation R series equals to R1 plus R2. And what is the first resistor? Why am I ending at R2? Because I only have two resistors in series. Thus, R1 plus R2 should give me the 2 ohm plus the 8 ohm, which as a result becomes 10 ohms. So this is R series, but also the total resistance. Okay, now what does B say? I hope you're all fine with the first one. So B says calculate the reading on A2. So what do you notice about A2? So you notice that A2, right? What did you say about A2? We say that A2 equals to A1, and A2 registers the total current. So A2 reads or rather measures the total current. Thus, as a result, please, another important tip. Every time you want to calculate something total, you use something total. Okay, now journey with me. If I want to calculate the total current, I am then going to use the total voltage as well as the total resistance. Similarly, if I want to calculate the total voltage, I must use the total resistance as well as the total current. Similarly, if I want to calculate the total resistance, I am supposed to use the total current and the total resistance. So in this particular case, I will then have something like this. So if I want to calculate A2, what do we know about A2? We know that A2 registers the total current, right? Therefore, I must use the total resistance and the total voltage. So I'm then going to use Ohm's law. Remember that Ohm's law says R equals to V over I. But that's not just any R, that's not just any V, that's not just any I. So it's going to be R total equals to V total. Why? Because I want I total. Use your totals to get your totals, right? Similarly, if you want to calculate the voltage across, say you have a resistor that's 2 ohms, and you want to get the voltage across the 2 ohm resistor, you must use that voltage because that voltage is corresponding or rather goes hand in hand with that particular 2 ohm resistor. I think this the last question will show us how that is, right? So in this particular case, what do I have? So my R total was calculated as 10 ohms, and my V total, remember that my V total, what was it? My V total was 11 volts, right? So now I know that I'm sure that this 11 volts over here is my V total. Why? Because now I know that my analysis is helping me conclude. So V total is what? 11 volts, and I total is what I want. I then say I total is then 11 divided by 10. I hope you guys do see that, how I actually did that. So it becomes 11 divided by 10, right? So that would be, is it actually 11 divided by 10? Let's see. It should be. So if I turn both sides, so if I make this 1 over 10, then this one must be IT over 11. Then I multiply both sides by 11. Yes, so that should be 11 over 10. Okay, just making sure. Can never get too um, um, fast with these things. So I total would then be 11 divided by 10, and that would give me a value of 1.1 amperes. This is the total current because it is the current for A2, right? Okay, so now because you've seen that, if they had to ask you for the current through A1, I hope you guys would actually agree with me when I say that A1 would also be 1.1 amps because A1 is equal to A2. Alrighty. So I'm just going to erase this because I just want to split this thing here. In fact, I'm just going to make these a bit small. Okay, just a bit small. Okay, there we go. Okay, there we have it. Right, so now I can get to the last question. So the last question, C, says to me, I need to calculate the energy dissipated by the 8 ohm resistor. So I want the energy dissipated by the 8 ohm resistor. Very important. You see, they are being specific. They are saying you must focus only on the 8 ohm resistor. As a result, what do? We say, if I'm looking at the 8 ohm resistor, remember, if you want something total, what do? You use everything total. So, total current, you use total resistance and total voltage. And in this particular case, you want the energy across the 8 ohm resistor. So if you're focusing on 8 ohm, you must use everything 8 ohm. That is, you must use the 8 ohm resistor as well as the voltage across the 8 ohm resistor. I really hope you guys can see that. So the 8 ohm resistor, right? So you have the 8 ohm resistor. That means if that's your focus, then you must use everything 8 ohms. That means V2, I hope you guys agree with me when I say V2 is the voltage only for the 8 ohm resistor. Remember, every voltage has its corresponding resistor unless it's the total voltage. So in this particular case, I know that if I want the energy, I need to eventually use the equation V equals to W over Q. But I don't have this guy, which is what I want, obviously. I don't have V and I don't have Q. So my goal is to first get V, get Q, then come back to this equation. So we're going to do that, right? So how do I get my Q? Well, I can use I equals to Q over delta T. So what is my I? My I is the current. Now, question. Do you think that the total current would be the current through the 8 ohm resistor? Aha, if you said yes, be very proud of yourself. Why? Because we analyzed and we've actually realized that the current through the 8 ohm is the same as the one through the 2 ohm, and they both read the total current. Okay, so from there, what do I then do? I then say, okay, now I can then say the total current was 1.8, and then Q is what I want. Sorry, that's 1.1, not 1.8. That's 1.1. Sorry, let's see. So that's 1.1. And what exactly is my time? I was given 4 minutes, right? How do I convert? Sorry. So that's 4 minutes, right? So how do I convert minutes to seconds? Remember, time in physics must be in seconds. I multiply by 60 because in a single minute I have 60 seconds. Therefore, what is the charge? The charge that I calculate will then be 1.1, right? So that's 1.1 times 4 times 60, and that gives me an answer 4 times 60 of 264 coulombs of charge. Right. So now I have the charge. What do I need? The voltage, right? So I need to then get V. What do I notice? Like I said, I am focusing on the 8 ohm resistor. That means I must use everything 8 ohms. So I then say, according to Ohm's law, R equals to V over I. What is my resistance? My resistance is 8, right? Because they want us to get the energy by the 8 ohm resistor. What is our voltage? Like I said, for every 8, for an 8 ohm resistor, you must use everything 8. What is the corresponding resistor for the 8 ohm resistor? If you said V2, you are correct. So that is V2. And what do I have as the current? The total current, which is 1.1. So V2 has a reading of 8.8 volts. Okay, so that is the reading on the 8 ohm resistor. Now I can then get my W, right? Because now I have V and Q. I can then say, okay, I know that V equals to W over Q, but not just any V. So this should not just be any V, but it should be V2. And we got that as 264, and we multiply that by oh, sorry. I'm so sorry. That was not that. I actually swapped the numbers. So that's 8.8 times 264, and that gives me a value of 23,000. Oh, sorry. So that's 2,232.2. I forgot this decimal thingy, so that's why I was on some 23,232. There's a decimal there, guys. So just a little blunder. Okay, so what is that? W. What do we know about W? That's energy, so that's measured in joules. So that, ladies and gentlemen, is the work, or rather the energy dissipated by the 8 ohm resistor. And just out of curiosity, if you had to determine V3, what would you do? Remember, V3 is has its corresponding resistor, 2 ohms. So for V3, I must use the 2 ohm resistor. So if I want V3, I would say V3 equals to, in fact, according to Ohm's law first, right? So according to Ohm's law, R equals to V over I. But not just any V, V3. And not just any R, but the R of the 2 ohm resistor. And that is divided by the current, which is the total current, because the 2 ohm resistor reads the total current. Therefore, if I wanted to get V3, I would say, what is the 2 ohm? So the reading for the resistance is 2, and the reading for the total current should be, what is it, 1.1. So V3 should be 2.2, right? So V3 is 2.2. That's the reading on V3, 2.2 volts. Now, out of curiosity, like I said, if you wanted to see something, is it actually true that the sum of V2 and V3 gives me V1? So let's put that to the test. So what is V1? V1 is 11 volts. So what do? We then say V1 equals to V2 plus V3. So V2 is, what do we get as V2? I think that's 8.8. And for V1, we get a 2.2. So what's the sum of that? 8.8 plus 2.2, that gives me a value of 11 volts. Right, so that is actually V1. Do you guys see that? So V1, which is the total voltage, is the sum of the individual voltmeters. In the previous video, we had something like this. This was for a series circuit. Hope you guys are seeing that. I really hope you guys are seeing that. Okay. Um, all right, so that's V1 is 11 volts, and we've actually proved that to be true. Okay, so that will be the law, the end on a parallel, on a series circuit. So I want us to just look at now a parallel circuit. Okay, right, so just before I look at the parallel circuits, I just wanted you guys to know something, a very important point. Just gonna make that a young NB. So it's just gonna be an NB, a nota bene. So an NB that I'm gonna make now is that you must remember that in a circuit, if you have a closed switch, right? Some of you might probably know this. If you have a closed switch, if you have a closed switch, what does that mean? So if you have a closed switch, you then introduce what you call your EMF. You get what you call an EMF, which I like to call an EMF. So you get what you call an EMF. So what is an EMF? So EMF stands for electromotive force. So EMF is electromotive force, right? So what is EMF? So when you have an open switch, sorry, why did I say closed? I meant open. So sorry. It's supposed to be an open switch. So when you have an open switch, what does that tell you? An open switch basically tells you that no current is flowing at that particular moment in time, right? So what you do always, if you have an open switch, whatever the reading on your EMF will be. So if this is true only for an open switch, I'm just going to write that open switch. Please do not forget this. Open switch, not a closed switch, but an open switch. So in a circuit, an open switch would be something like this, right? Because now there's no current flowing. And then obviously your closed switch, oh, okay, that's array. And then for your closed switch, you would have something like this, right? So that's where your current can flow. I don't know why I had that, but because I'm assuming most of us know that, but I mean, for interest sake. Okay, so an open switch, right? That is when you say that your EMF is equal to the V total. So your voltage across the entire circuit is equal to the EMF. So if you have an open switch, so the EMF is read as the voltage across the entire circuit. That is if and only if you have the open switch. That means no current is flowing, no flow of current. Okay. Um, by the way, that is a very important point that you guys must not forget. All right, so moving on. So we have to get to the parallel circuits, right? So looking at this particular parallel circuit, so they say, so this is example two, right? So looking at example two. So under example two, what do I have? So under example two, I have a certain circuit such as this one. So it's like this, like that, and like that. And it has, sorry, and it has an ammeter here, which, sorry, so that's A, so that's ammeter A, and it's connected to a 6 ohm resistor. And as it's connected to a 6 ohm resistor, we have again here, in fact, we should have a, oh, sorry, let me just do that. Now we have, whoa, what just happened there? I always have trouble drawing these things. I just want to be careful when I draw them. Okay, so this would be a switch S, and it would have another resistor here, and that would be the 3 ohm resistor. So that's 3 ohms. That is connected to the 6 ohm resistor. Let's just go down. There are other resistors here. So that would be a 4 ohm resistor, and that would be a 6 ohm resistor. Sorry, that's not a 6, that's an 8 ohm resistor. Okay, so now that you have your 8 ohm resistor, what do we then see? I'm just going to push this thing up a bit, or rather, let's do this. Oh, what just happened there? Okay, I think I'm just going to do this for the sake of my sanity. This thing is just going to drive me crazy. I'm just going to push that out there. Okay, there we go. Right, so we have our, by the way, this is a combination circuit. You guys will see why. Right, remember, I'm not gonna write down the questions first because I want us to first analyze, right? In fact, it's best if I just write down the questions, but we will not answer them before we analyze. Guys, please promise me and yourselves that you will always analyze your question before you look at the answer, before you start answering. Analyze your diagram. So in this particular case, the first question wants me to determine the total resistance, the total resistance, right? The total resistance. And the second one wants me to calculate the reading on the ammeter, the reading on A, reading on A. And the third question says I need to determine the energy, right? So it wants the energy dissipated by the 8 ohm resistor, right? So it wants the energy dissipated by the 8 ohm resistor in exactly 2 minutes. And so these are the questions that we must focus on. But remember, before you answer any question, look at the analysis. Oh, and by the way, I have a voltmeter across the battery, and this guy here reads 14 volts. So that's a voltmeter V, and he reads 14 volts. Right. Okay, I think now we can start analyzing. So now what do we notice? Remember, V is the voltage across the battery. Does that actually mean it's the total voltage? Yes. So this guy will basically read the total voltage. So I am analyzing my diagram, right? So it's the total voltage across the entire circuit. Aha, there you go. Right. And then they say, right? So now, okay, besides the then they say part, now we start analyzing. So notice that we have a positive terminal here. Ah, terrible, terrible, terrible. We have a positive terminal here, right? And then we have our negative terminal there. So what does that mean? Current to flow in this direction. Now, this is the part that I want us to focus on. So notice something. Just before the current starts to continue flowing to other parts, it reaches this point right there. What I like to call that point is the point of splitation. Might sound like a pretty weird name, but I really like the name actually. Kind of makes sense if you ask me. So this is what we call the point of splitation. I like to call it rather. In fact, I also recommend my students to call it that because it kind of makes sense if you ask me. So it's the point of splitation. I'm going to explain why. Splitation, not splitation. Um, the point of splitation. Now, why is that? Because if you think about it, right, this point, that very point, is the point where current starts to split. Right? So this point here in particular, That is the point where current starts to split. That is why I call it the point of splitation, right? Because it's the point where current starts to split, hence point of splitation. So what happens when current splits? This is where current will start getting divided inversely, as per the notes that we had on our first video, right? We said that current in a parallel circuit is divided inversely. How do we know that a circuit is parallel? Immediately when your current starts to divide, that's when you can conclude that your circuit is parallel. Once your current starts to divide or to split, rather, once your current starts to split, then you can say you have a parallel circuit. I mean, if you look at the previous circuit, the one that we had here, there was no split of current. That is why we said that we have a series circuit. But in that particular case, this particular case right here, we have a split in current. Remember, point of splitation, right? That means that if I have a point of splitation, that's where my current starts to split. Thus, as a result, I have a parallel circuit. Now, current flows inversely. It is split inversely, right? So my current will move in this direction, and there's going to be current that also moves in. In fact, let me use different colors for those currents there, just so you can see, just so you can get an understanding. That there's going to be current flowing in that direction, and there's going to be current flowing in this direction, right? Just like that, and like that, like that, like that, like that, like that, like that, and there's going to be current flowing in this direction, like that. Once you get to that point, you realize you have another point here. This point is now called, what do you think is going to be called? It's called the point of togetherness. So this point here, I call the point of togetherness. I mean, as you're sitting right there, you're probably saying, ah, these are some weird names. What do you mean togetherness? Well, the reason I call it the point of togetherness is because that is the point where my current starts to come together. The split current starts to meet once again, right? When you have a friend that moves to another city, so 2025, your friend moves to another country, and you guys are separated, you guys are split, best friend split. In 2035, 10 years later, you guys meet again, right? So you guys had a certain rendezvous point. So you have a rendezvous point maybe at some park, and your friend comes back now with his own car, wealthy and everything, right? And you guys meet at the same rendezvous point. That may be a certain area in a park or something, right? So you guys come together once again. So the current split at this point here, the point of togetherness, and it came together once again here at the point of togetherness, right? I mean, some of you might actually see these words as quite crazy, but it kind of helps and kind of makes sense if you ask me, right? So notice something. At the point of togetherness, the current comes together again and continues to then flow as the total current through that switch, right? So what I want you to take from this is that current before a split is registered as the total current. Just before a split, you have the total current. So, with that being said, you guys agree with me when I say that A reads the total current. So, this guy would read the total current. Why? Because just before the split, we had emitter A. Do you also agree with me that through the 3 ohm resistor, this guy here, through that 3 ohm resistor, we have, sorry, there was a little mistake. So through the 3 ohm resistor, we also have the total current. I hope you guys are seeing that because just before a split, so please note, just before a split, you have the total current. Just after the point of togetherness, you have the total current. So in this particular case, what do I have? I have, okay, for starters, I'm writing down my observations. I then realize that A reads the total current. Remember, the total current is the current just before a split in a parallel circuit. And then similarly, the current through the 3 ohm resistor, so R 3 ohms, also reads the total current. Right, now that we've gotten that out of the way, we can continue to analyze and so on and so on. Now remember, what do you notice about the lower division in the circuit? Aha, you notice that the 8 and the 4 ohm resistor both have the blue arrows flowing through them. Remember, the blue arrows are the one in the bottom division. So in the bottom division, you have the 8 ohm resistor and the 4 ohm resistor, and they have the same current flowing through both of them. That means you can then conclude that the 8 ohm resistor, the 8 ohm, and the 4 ohm are in series with each other. I hope you guys are seeing that. Why? Because they have the same current flowing through them. They have the same current through both of them. I really hope you guys are seeing that. Please tell me you guys are seeing that. Right? So the 8 ohm resistor and the 4 ohm resistor are in series. So R8 ohms, R8 ohms and the R4 ohms are both in series with each other. Right? So the 8 ohm resistor and the 4 ohm resistor are in series. Why? Because they have the same current. But what do you notice? The green part, the first division right here, this part here is the green part. That's the first division, right? The first division has green arrows. That means that the current through the first division is definitely not equal to the one in the second division. But what do you notice? Notice that since the current was split, remember I told you, a split of current tells you that the circuit is parallel. Do you guys agree with me that now that we've seen that the 8 ohm and the 4 ohm are in series, do you agree when I say that the 6 ohm resistor is in parallel with the 8 ohm as well as the 4 ohm resistor? So it's in parallel with the sum of the two. Now remember, if you had to get the resistance of this portion here, so if you had to get the resistance here, you would obviously see that they're in series. So you'd say R series equals to the 4 ohm plus the 8 ohm, which would give you the 12 ohm. And that 12 ohm resistor, because it's the sum of these two guys, that 12 ohm resistor will be parallel to the 6 ohm resistor. I really hope you guys are seeing that. So that 4 ohm resistor and the 8 ohm resistor are in series, right? So the sum of both of them will then be parallel to the 6 ohm resistor. So 4 ohm and 8 ohm are parallel to the series. Sorry, 8 ohm and 8 and 6 sorry. Let me take a breather. The 8 ohm and the 4 ohm are in series, but the sum of the 8 ohm and the 4 ohm are in parallel to the 6 ohm resistor. Why is that? Because the current flowing through the 6 ohm is not the same as the one flowing through the 8 and 4. Therefore, they are parallel to each other. What did I say? The moment you notice a split in current, you can then say that your circuit is parallel. Therefore, the 6 ohm resistor is parallel to the the R4 4 ohm resistor and the R8 ohm resistor. Therefore, what about the 3 ohm resistor? Do you guys agree with me that the 3 ohm resistor is in series with the parallel division? What I mean is, if you had to get the total resistance in parallel, that particular resistance would be in series with the 3 ohm resistor. That means if I had to say the sum of 4 and 8, remember those are in series, and then I get the R series to be 12 ohms. And since 12 is parallel to the 6, I then use the 1 over RP equation. And then let's say I get a value of RP being 8 ohms, right? So that 8 ohms, by the way, it's not going to be 8 ohms. I'll tell you why. So that particular 8 ohms will then be in series with the 3 ohms resistor. Why? Let me show you. Let me actually quickly just draw a little diagram for you to notice what I mean. So what you would typically see is that these guys here, right? So this is how I'm going to take this portion here. This portion here, I will take it and make it one resistor. So let's say I get the total resistance in parallel and I get it as 3 ohms, right? So that's the total resistance in parallel. That's the 4, the 8, the 6, okay, the 4, the 8, and the 6. If I want to make that one resistor, I then need that's going to be the 3 ohm resistor. Therefore, I'm going to form a new circuit, something like this. So that's going to be my A, bonded to, I mean, connected rather, just think of chemistry, to the 3 ohm resistor, and then connected again to another 3 ohm resistor. So what do you notice? You would notice that this guy here was formed from this entire part right here in the division. So this entire division formed this 3 ohm resistor, right? Therefore, as a result, if that is the case, just add my ohmic sign there. If that is the case, then you can see now that a combination of 6, 4, and 8 gives me 3 ohms. Thus, the combination of 6, 4, and 8 is in series with the 3 ohm resistor over there, right? So, I can then write that down. I can say that um, R parallel, that would be the resistance in parallel. So R parallel is in series, to the 3 ohm. Because now if you had to show the flow of current in your new circuit, you'd notice that they share the same current, right? I know this may be a lot to take in, but if you can just journey with me, I promise you it will be very comprehensible. Okay. Is there anything that I need to now analyze? I think my analysis is enough. Oh, and by the way, just a quick tip. If you are actually not sure in an exam, right, about whether or not your resistance in parallel is correct, you must know that the resistance in parallel, the total resistance in parallel, must be lower than the lowest resistor. I will repeat. The total resistance in parallel must be lower than the lowest resistance, right? So notice how, if I had to form a new division, so I would take the 6 ohm, right? So I would have something like this. So there's my 6 ohm resistor, right? And that would be in parallel to a 12 ohm resistor. Now, where does that 12 ohm resistor come from? That's the sum of 8 and 4. Since those two are in series, I took them and I made them one resistor. So if I had to determine the total resistance in parallel, so if I had to determine RP, RP must be smaller than 6 ohms. So the total resistance in parallel must be lower than the lowest resistance. In this particular case, this is the lowest resistance, right? Therefore, RP must be lower than 6 ohms. So as you do the question, I'm going to come back to this and actually show you that it's actually true. It actually makes sense, right? What's 6? Why is there 6 there? Why did I put that there? But anyway, that's minus 6. So now we can start answering the questions, right? So now we have question A, which says it wants, what does it want? The total resistance. The total resistance of the circuit. They're not specific. They didn't say the total resistance in parallel. No, they want all the total. They want the total resistance in the circuit. So that is the 6, the 4, the 8, and the 3. But what do you know about the 4 and the 8? Remember your analysis told you that they are in series. Therefore, I can now use my series equation and I can say that R series is equal to R1 and R2. I end there because there are only two resistors that are in series, and that's the 4 and the 8. So that's 4 plus 8, and that should give me 12 ohms, right? So that is the resistance in series. Now, what did I say again? I said that this guy, the 4 ohm and the 8 ohm, are in parallel to the 6 ohm. Now I can use my parallel equation and I can say that 1 over parallel, Rp parallel resistance parallel equals to 1 over R1 plus 1 over R2. Now that would be the 1 over the 12, which is the resistance in series, right? So that would be 1 over the 12 plus 1 over the 6. And that should give me, so 1 over 12 plus 1 over 6 gives me an answer of 1 over 4. So that's 1 over Rp. Now remember that we want Rp and not the inverse of Rp. We don't want 1 over Rp, we want Rp. So we go Rp, we flip both sides according to mathematics. What you do on the left, you do on the right. Therefore, Rp will then be 4 ohms. Right. Now notice something. This guy right here is 4 ohms, right? When you did your calculations in this part, who was your lowest? Which number was the lowest number? Aha, 6, right? And remember, I had said that to check that your total resistance in parallel is correct, then the total resistance in parallel must be less than the lowest resistance. So notice that Rp in this particular case is actually less than 6 because Rp is 4 and 4 is less than 6. Therefore, the total resistance in parallel must be lower than the lowest resistance. Okay, I really hope you guys are actually seeing that. Now we want the total resistance. Are we done? No. Now we know that if I want R total, according to my analysis, what do I see? I notice that Rp, right? So Rp is in series to the 3 ohm resistor. So that means I can say that Rp, sorry, not Rp, but R total. So I can then say R total equals to Rp plus the 3 ohm resistor. Therefore, that's going to be 4 plus 3, and that gives me the total resistance of, oh, sorry, the total resistance, the flow of 4 plus 3 should be 7 ohms. Right, I really hope you guys got that part right. Okay, well, that is that, and that is how we conclude that question. So that is our total resistance. I really hope you guys are actually following on how I'm actually answering these questions. Again, your analysis, very, very important, right? So now they want the reading on A, right? Okay, so they want the reading on A. Sorry, that's supposed to be question B. Right, so question B should be the reading on A. So what do we know about A? So we know that A reads, remember, the total current. So that tells me that I want the total current. So that tells me that I want I total. What did I say in the first in the previous question? If you want something total, aha, you use everything total. There we go. So I can use Ohm's law, right? So I can then say R equals to V over I, but not just any I, right? So this is, I'm going to rewrite this as R total equals to V total over I total. So that should then be, what is V total? The total voltage, remember we said according to our analysis, it is the 14 volts because it's the voltage across the battery. So that is going to be then 14 divided by the wait, no, hold on. I think this is why I always want to write things underneath each other. So I want the total current. So you guys would notice that my I total would then be Sorry, I wrote the equal sign twice. My I total would actually be can I just fix that? So my I total would then be VT over RT, right? So that's VT over RT. And I think you guys also might be familiar with this triangle, right? This triangle that looks something like this, where we say there's an R there, a V there, and an I there. So in this case, we are looking for I, so I is V over R, right? Some of you may be familiar with that. So that's why I have VT over RT. So now I can calculate my total voltage was 14 and my total resistance was calculated to be 7, right? So that is 7 and I divide it and I get 2 amperes. So that is my total current. So my total current is actually 2 amperes, right? And that is it. And then the next question wants us to calculate, I don't know what. Let's actually go and see. So the next question wants the energy dissipated by the 8 ohm resistor in 2 minutes. So let's actually go to that. So there we go. We go the energy dissipated by the 8 ohm resistor in 2 minutes, right? So we then say, what resistor we're looking at? Okay, there we go. Sorry, I lost my train of thought. So that would be the 8 ohm resistor. Now, notice how we are focusing on the 8 ohm resistor. That means we must look at everything 8 ohms, right? Aha. So this one is going to be quite lengthy because a lot has to be done here. That is why this question is 5 marks. Why? Because now you need to think very critically about this one. Now, remember, you said that this circuit was parallel and you stuck to that conclusion, which is true. Now, you must think about it. If you had to introduce a voltmeter here, say V1, right? And you had to introduce another voltmeter here, say V2, and you had to introduce another one here, say V3. Do you guys actually agree with me when I say that V3 is equal to V, which is the total voltage? So V3 equals to V total. Do you guys agree with me on that one? Now, why is that? Remember, we said that in a parallel circuit, the voltage is the same everywhere. Guys, we said that here. That's when we came up with this equation, right? So in this particular case, what do we notice? We notice that V3 is equal to V total, but V total equals to V1 plus V2. Or you could say that V3, which is also V total, is equal to V1 plus V3. Why? Because the 8 ohm is in series with the 4 ohm resistor. They both have their corresponding resistors. What do you know about resistors voltmeters in series? Remember that voltmeters in series have they're divided proportionally, meaning the higher the resistor, the higher the voltage, right? But the main idea behind this is to actually go and see that. Remember when we did this, we said that this is true. So V total would be the sum of the individual voltages. So V total, which is also V3, so what you can say is that now that V3 equals to V1 plus V2, right? Because V3 is also equal to V total, right? So let me first start there. So V3 is equal to V total. Therefore, V3, right, which is for the 6 ohm resistor, V3 is for the 6 ohm resistor, that is equal to 14 volts as well because it's equal to the total voltage, right? Hope you guys see that. So that's also going to be 14 volts, right? Just about there. So that's also going to be 14 volts. So that's V3, 6 ohms, 14 volts, right? And then V3 is V1 plus V2. So V3 is V1 plus V2. Do we have V2? Hmm, no, we do not have V2. Do we have the current through that particular division? No. Okay, so I just realized something here. So as I'm looking at this question, I realized, okay, what do you notice? I have another 3 ohm resistor here. So that 3 ohm resistor, remember, it's in series with the parallel division. So I actually made quite a huge blunder here, guys. I'm so sorry. V3 is not equal to V total. I made a very huge mistake here. Why? It would have been, right, if and only if the 3 ohm resistor, this guy here, if this guy was not present, then we could have actually said that V3 equals to the total voltage. But remember, the total voltage would be the sum of the voltage across the parallel division plus the voltage across the 3 ohm resistor. So what you can do is to say, okay, how about I get the voltage across. Let's see. So if we can look at if we can look at the thingy, we can get the voltage across the parallel division because we have the resistance. Remember, we calculated that resistance, and we got um, what was the voltage across the parallel resistance? We got 4 ohms, right? Yes. So V R parallel was 4 ohms, and we have the current flowing through the 4 ohm resistor. Because once we make it one resistor, it reads the total current. So like I said, with my initial drawing, I had my A here, and then I had my resistor here, and then I had my 3 ohm here. So this would be the 12 ohm resistor, right? Sorry, not the 12 ohm, but the 4 ohm. Remember, that's the 4 ohm resistor in parallel. So this 4 ohm resistor would then read the total current. Aha. So if that is the case, what do I then do? So I then say, okay, um, how about I say, according to Ohm's law, which is R equals to V over I can say that the resistance across the parallel division, right? The resistance across the parallel division, I want to get the voltage across the parallel division. So that's V parallel. And I then gonna use I total because it then uses the total current. That means if I want VP, I know that VP is RP times IT, right? And that would then be the 4 ohms times the 2 amperes, and that would give me 8 volts, right? So that would give me 8 volts. And then what do I then do? I then say, okay, how about I actually get the current through the second division? So notice something. That's what I can do. I can get the current through this division, right? Because I have the resistance, I have the voltage, sorry, I can now get the current, right? So if I make these two whole, if I make them one resistor, what was that resistor? The 12 ohm resistor. So I can then go again and use Ohm's law, and I could say, according to Ohm's law, um, I want to give it like a name or something. So I want to say, so how about we name it? So let's try naming it. So this portion here, we can name it. Let's make it RB for R below. Um, Honestly, the naming part in an exam, I really think would be very important that you actually make very good. How can I actually place it? Make sure that when you name it, at least have a key for the marker to actually see that RB is basically the resistance in the bottom division. So we'll just call that RB, right? So you're gonna, if you do something like this in the exam, please at least have a key so that the marker can actually see that, okay, RB is the resistance in the bottom division, right? And then so now we're gonna say RB is gonna be equal to the current, so it's going to be the voltage in parallel divided by the current that we want. So the current in the bottom division, right? So I then say the resistance was 12, the voltage parallel is 8, and I want the current. I then say IB, I hope you guys can see, according to my some mathematical gymnastics, you should get this answer as 8 divided by 12, and that gives me 0.67 amperes. I just want to make it 667 because it's not the final answer, so we're just trying to avoid any rounding off errors. Right, so that is IB. That's not a 6, by the way. That's a B. I think I'm going to make it a capital B. So that is IB, right? So that's the current through this bottom division here, this RB here. Not the 6 ohm, no, but the bottom division, right? So what I can do is now that I have the current and the resistance, I can now get the voltage. But now remember that the voltage for the 8 ohm resistor plus the voltage for the 4 ohm resistor must be equal to the voltage. Is it the voltage in parallel? Let me actually see that. Yes, so it must be equal to the voltage in parallel because the voltage in parallel is for the entire division. So V3, right? So V3 would basically be equal to 8 ohms, right? Sorry, V 8 volts, not ohms, 8 volts. V3 would be 8 volts, right? So I'm going to write that down. So V3 would be 8 volts. And then that 8 volts would be equal to V2 plus V1, right? So that basically means that 8 volts would be equal to the voltage across the 8 ohm as well as the voltage across the 4 ohm. So that is going to be equal to 8. Do I have the voltage across the 8 ohm? No, but I'm just going to keep this equation in mind. So I'm just going to box it because I might come back to it. Okay, so that's what we know, right? Now let's go back to our diagram. What else can we deduce? What else can we say? Right, so now that we've noticed that we have the current flowing through that particular division, you guys should see that since the same current that flows through the 4 ohms is the same one that flows through the 8 ohms. Thus, it is safe to say that I can then get V1 because I have the resistance, which is 8, as well as the current flowing through the 8 ohm resistor. In fact, this box thing was not necessary now that I look at it. So V1, which is the one for the 8 ohms, in fact, let me just call it V8 ohms, right? In fact, let's just use according to Ohm's law, right? So according to Ohm's law, R equals to V over I. So that's going to be the resistance, the 8 ohm, and that's going to be the voltage of the 8 ohms, and that's divided by the current in the second division, which is IB, which is what we calculated here. So then that means if I want V, right, which is V1 or V8 ohms, I would then say V8 ohms. What's the that's going to be R8 ohms plus, times IB. And that's going to be R8 ohms was basically 8 ohms times 0.67. What? Okay, so that we said that's 0.667 to avoid any rounding off errors. So that's 0.667. And we get an answer of 8 times that. That gives me 5.33. 5.33 volts, right? So that gives me 5.33 volts. Okay, and then out of curiosity, if we had to determine V4 ohms, so we say V4 ohms would be equal to R4 ohms times IB, right? Because they have the same current. So that would be 4 times 0.67, right? And that should give me 4 times 0.667, and that should give me an answer of 2.668. Okay, so that would be 2.668 volts. So I said that, remember, let's see if these two actually give me VP, which is 8. So V4 ohms plus V8 ohms must give me, so that's going to be 5.33 plus 2.668, right? So 2.668 plus 5.33 gives me 7.998, which is someone basically 8. The reason it doesn't give you an exact value 8 is because those numbers are basically rounded off, but you just see that it gets basically, if you round that number off, you get an 8. So what we said is true. But we are not asked to calculate any of this. well, not the 4 ohm resistor one. Now that we have the voltage across the 8 ohm resistor, I can then say V equals to W over Q. But do we have charge? No. But do we have current? Yes. So we have the current through the 8 ohm resistor, right? So we can say IB equals to V of the 8 ohm resistor, so not V, but the Q, because it's charged, right? So that's going to be Q divided by time, right? So what was IB? That was 0.667. The charge is what I want. And my time was, what was my time? My time was 2 minutes, right? So that's 2 minutes times 60. And I get my charge as 0.667 times 120, and that gives me ooh, an answer of 80.04 coulombs. Now I can go to the V equals to W over Q. And I can say now confidently that V 8 ohms equals to the work done over 80.04. And that should be work done equals to that's V 8 ohms times 80.04. So that should give me a value of 5.33 times 80.04 is a value, so my W will then be 80.04 times 5.33, and that gives me a value of 426.94. And now if I look at this, I think about the rounding off error. So let's try to basically be very accurate. So instead of just rounding off this final answer, how about I just write down the answer? So let me see, what was the answer before? So it's 80.04, right? So let's make this, so what I'm gonna do is I'm gonna try to basically write answers as fractions, just so to avoid rounding off errors. Guys, please, rounding off errors is the last thing we want. So that was 8 over 12, right? So that was my IB. Just gonna write it as a fraction. So my IB was 8 over 12, and then I can say that 8 over 12 times 120, that gives me an answer of 80, right? So that's 80 coulombs. Cool. I can then say 8 divided by 12, that's 0.66. 8 divided by 12, that's 0.666667. Right, so that is my charge, 80 coulombs. Right, so notice how it just changed because now I just chose to just write it as fractions to avoid rounding off errors. So that's V 8 ohms, right? So I'm just going to remove that. I'm just going to put my Q down there. So that's Q, and that's multiplied by Q. So that's my V8 ohms. So that was 8 times 8 over 12 basically. So that's 8. um I mean, what I mean by that is that if you look at this, remember this is IB, and IB is a fraction, is something like 8 over 12. So that would be 8 times 8 is 64, so that's 64 over 12. That's what V8 ohms is. So V8 ohms should be 64 divided by 12 times 80. And that should give me an answer of, let me see, 64 divided by 12 multiplied by 80. That gives me an answer of 200, that gives me an answer of 426.67 joules, right? And by the way, if you could maybe do this different on your own, you'd notice how my answer would differ from yours. So yours would maybe be like 430. Why? Because of my rounding off, right? So I quickly just rounded these numbers off. Thus, there was a lot of a few mistakes that were made. So please just try your best to maintain these things as fractions, just to avoid rounding off too quickly, right? So that's like the best thing you could do, just to avoid rounding off too fast, right? That's then the end of this question, and the end of a very lengthy video. I did not see that, but anyway, um, Now that we've finished both these questions, I really hope that we are all fine with everything. I hope that no one is lost anywhere. And if you are, please drop down a comment in the comment section or send me an email and I will make sure to get back to you. But from me to you, I will see you in the next video. Bye bye.